Good morning, children. This is class 12th physics. We are doing the chapter number 6, electromagnetic induction. Today we are going to cover the topic that is mutual induction and mutual inductance. Now, children, here we can see that there are two coils, right? So the coil with which the battery is connected is your primary coil. That is, the coil in which the current is produced is your primary coil, and the other coil which is placed very near to the primary coil is your secondary coil. So this is your secondary coil, right? So here, children, the current, if we vary in the primary coil, if we are changing the current in the primary coil, then the magnetic flux which is linked with the secondary coil, which is kept very near to this, right? The magnetic flux linked with the secondary coil will change, and we know, according to the electromagnetic induction principle, if the magnetic flux linked with the coil changes, then induced EMF will be produced in the secondary coil. So this is your mutual induction. So how we can define mutual induction? So mutual induction can be defined as when an induced EMF is produced in the secondary coil. Why? Due to the change in the current in the primary coil. Then this phenomena is known as mutual induction. Right, children? So this is the property of the two coils. This is the property of the coils, because of this property, it is going to oppose the change in the current. It will oppose any change in the current flowing through it by developing an induced EMF, with the help of an induced EMF, right? So children, suppose here we are having two coils. Let the coil which is connected with the battery, be called primary coil P, and the other coil is the secondary coil, which is kept very close to the primary coil. Now what will happen? On pressing the key, on putting this current source on, the current in the primary coil will increase. So as the current increases, the current will increase from 0 to some maximum value, right? So it will increase from 0 to some maximum value. So as the current is increasing in the primary coil, the magnetic field will also increase in the primary coil, and the magnetic flux will also increase in the primary coil. But the secondary coil is kept very close to the primary one. So the magnetic flux that is linked with the secondary coil, magnetic flux, we know it is denoted by phi. So phi 2, that is the magnetic flux which is linked with the secondary coil, will also change. And we know, according to the electromagnetic induction principle, if there is change in magnetic flux, then what will be produced, children? Yes, induced EMF or current will be produced in the secondary coil. And so the galvanometer, if we connect here a galvanometer, the galvanometer showed the momentary deflection. Right, children? Now, the direction will be such that it will oppose the increase in the current. Similarly, let's talk about the other way out. Suppose the current is flowing through the primary coil. Now we just switch it off. So when we are switching off, the current value will decrease. It will go from some maximum value to 0. So it will take some time, right, children? So during this time, as the current in the primary coil, let us call I1, as the current is decreasing, the magnetic field in the primary coil will decrease, and the magnetic flux in the primary will also decrease, plus the magnetic flux in the secondary coil will also decrease. So as the magnetic flux in the secondary coil is decreasing, it is changing, and induced EMF will be produced in the secondary coil. And according to the Lenz's law, the induced current that will be produced will oppose the decrease in the current. Right, children? So this property of the coil, this property of the coil that this property of the coil to oppose the change in the current is known as your mutual induction. So here you're having two coils, right, children? Now let's talk about mm, let's see how we are going to relate these terms. Now suppose, children, the strength of the current in one coil is I1. I1 is the strength of the current in the primary coil, right? Then the magnetic flux which is linked with the secondary coil will be phi 2. So children, we know that phi 2 is proportional to I1. That is, the flux in the coil 2 will be proportional to the current in the primary coil. So if we remove the proportionality sign, a constant will appear, and that constant is M, and it is known as mutual inductance of the two coil, or coefficient of mutual induction. Okay, children. So if we keep the value of current as 1, if here we keep as I1 as 1 ampere, then children, M will be equal to phi 2. So the mutual inductance of the two coil is equal to the amount of magnetic flux linked in the secondary coil when 1 ampere current flows through the primary coil. Right, children? So we know that the EMF will be reduced in it. Right? Now, children, here M. On what factors does M depend? This we will see slightly after the next slide. The magnitude of the induced EMF in the secondary coil is given as by the Faraday's second law, that is E2 equals to minus d phi 2 by dt, where d phi 2 by dt is rate of change of magnetic flux in the coil in the secondary coil, right? If we substitute the value of phi 2 from here, if we put the value of phi 2 over here, then it will become E2 equals to minus d by dt of Mi, but M is the mutual inductance of the two coil, but its value is constant. So let's take M outside of the differentiation, and finally we will get the induced EMF in the secondary coil, that is E2, is equals to minus M di1 by dt, where di1 by dt is the rate of change of current in the primary coil. Right, children? Now, okay, here we need to see that the mutual inductance, children, it does not depend upon the current. It depends upon the geometry of the two coils. That is, it depends upon the size and shape of the coil. It depends upon the distance between the two coils. Plus, it depends upon the medium between the two coils. And it also depends upon the number of turns in the coil, right? And this coil has been wrapped on some material, so it depends upon the material on which the coils have been wrapped, right? So these are the factors on which the value of mutual inductance depends. Now let us consider a special case, that is, we are going to derive the mutual inductance of two coaxial solenoids. Coaxial solenoids means they are having same axis. So you can see here one solenoid I have shown with some orange color, and the other I have shown with some white color chalk, right? So these two solenoids, they have been merged, right, children? So this here we are going to find out the mutual inductance for the two coaxial solenoid. So mutual inductance, now we know what is it. It is the phenomena of production of induced EMF. इसमें induced EMF produce होता है एक coil में, किस वजह से? Due to the change in the current in the neighboring coil, right? Now, the current flows in the primary coil and induced EMF or current is produced in the secondary coil, right? And we know mutual inductance, if the value of mutual inductance is more, then the phenomena of mutual induction will take place more, right? It means due to the change in the current in primary, more EMF will be induced in secondary if M value is more. Similarly, if M value is less, means mutual induction जो phenomena है, that will take place less, means due to the change in current in primary, less EMF will be produced in secondary. So that is your mutual inductance, M. Now here what we are considering, here we are considering that the two coils, over here the two coils, they are having the same cross-sectional area A and their length is also same, that is L. Right, children? Now, the current that is flowing through the primary coil, that is the orange coil, is I1. This current I1 will produce magnetic field B1. Right? This we know. Now, let the number of turns in the primary coil be N1 and the number of turns in the secondary coil be N2. Now children, the magnitude of the magnetic field, this magnetic field कितना produce होगा, that is given by mu naught N1 I1, where N1, small n1 is the number of turns per unit length. Total how many turns are there, children? In primary, total in primary N1 turns. What is the length of the primary coil? L. So number of turns per unit length will be N1 by L, capital N1 by L, right, children? Let's substitute this value of N1 over here. So we will get the magnetic field B1 equals to mu naught capital N1, that is the total number of turns in primary coil, I1, that is the current flowing through the primary coil, upon L, and L is the length of the primary coil. Now, because of this magnetic field, the flux will be linked with the secondary coil. Now, this magnetic field it will pass through the axis of secondary coil also, due to which magnetic flux will produce. So magnetic flux, children, we know magnetic flux is in the secondary coil will be phi 2. For secondary, we are using the number for denotation as 2. So phi 2 equals to N2 B1 dot A. Why B1? Because magnetic field is produced due to coil 1, because current is flowing in one coil, right? So if we remove the dot product, we are going to have here cos theta. Here theta is the angle between the magnetic field B1 and the area vector A. So if we look here, children, the magnetic field and the area vector A, they are along the same direction. So the angle between them is theta. Theta is 0. So cos 0 will make 1. Right? Let's substitute the value of B1 from here in this equation. So we will get N2 into mu naught capital N1 I1 upon L into A cos 0, and cos 0 will be 1. And children, here we will get phi 2 equals to mu 0 capital N1 capital N2 I1 A upon L. Now children, we know that mutual inductance in terms of magnetic flux, that is M equals to phi 2 by I1, right? This we know, we have done in the previous slide. M equals to phi 2 by I1. So let's substitute the value of phi 2 over here. So it will be mu 0 N1 N2. I1 will get cancelled, hai na beta? A upon L. So this is the value of mutual inductance when the material between the two coils, primary and secondary, is either air or vacuum. But if you replace the material by some other medium, then instead of mu, that is the magnetic permeability of the free space, you are going to put the magnetic permeability of that material. If it is air, then the value will be less, but if you put some another rod, then the value of M will increase. So here if we see, on what factors does mutual inductance depends? It depends upon the number of turns. More the number of turns in the solenoid, more will be the value of mutual inductance. More will be the area of cross section, more will be the value of mutual inductance. But it is inversely proportional to length. If the length is more, the value of mutual inductance will be less. So this is your mutual inductance of two coaxial solenoid. Right, children? Now next we are going to see about the coefficient of coupling. Coefficient of coupling. Now we know that when we place children two coils very near to each other, then due to the change in current in the primary coil and induced EMF, will be produced in the secondary coil, and this phenomena is known as mutual induction, right? Mutual inductance, right? Now the current, we know it always flows in the primary coil, and the induced EMF is produced in the secondary coil. But what will be the amount of mutual inductance? Kitna mutual inductance hoga? That depends upon that how much the magnetic field of primary coil is made available to the secondary coil. कितना magnetic field उसे available दिया है, कितना magnetic field उसके साथ linked है. So if the magnetic field B1 of the primary coil is completely linked with the secondary coil, then the mutual induction will be maximum and the value of induced EMF will be more. If completely the magnetic field is available to the secondary. If magnetic field which is available to the secondary is not completely, right, magnetic field agar mil hi nahi rahi, suppose you see this situation, here the magnetic field lines, they are not even crossing the secondary coil, so here the magnetic field is not available to secondary coil, so यहाँ पे mutual inductance induction होगा नहीं होगा, तो EMF reduce होगा नहीं होगा, right children? So the mutual induction, it depends upon the coupling. Mutual inductance ज्यादा होता है जब magnetic field are of primary are completely available to the secondary. Mutual induction कम होगा if magnetic field B1 of primary are not completely available to the secondary. So mutual induction, it depends upon the coupling, it depends upon the joining of the coil, it depends upon, we can say, the closeness of the coil. Right, so it can be shown by a constant that is known as the coefficient of coupling. Coefficient of coupling. So coefficient of coupling is denoted by the symbol K, and the coefficient of coupling of the two coils is the measure of the coupling between the two coils, right? How closely, how joint you have done, right? So it is the measure of coupling between the two coils. If the value of K is more, means the magnetic field B1 is completely available to the coil 2, and so the mutual inductance, the mutual induction will be more. But if the value of K is less, means magnetic field jo B1 hai, that is not completely available to the secondary coil, so mutual induction will be less. Right children? So it depends upon the value of K. So K, it measures what? It measures the availability of magnetic field of primary to secondary. Primary की magnetic field secondary को कितनी available है? That depends upon the value of K. That is the coefficient of coupling. Right. So here we are having few cases. In the first case here, as you can see, that the coil, primary coil and secondary coil, they are coaxially, they have been merged, means they are having the same axis. So here the magnetic field of primary is completely available for the secondary, so the coefficient of coupling will be 1. Second case, if you see, the magnetic field of primary is not at all available to the secondary, so the coefficient of coupling will be 0, and here the mutual induction will be 0, it will be very less, and here the mutual induction will be maximum. Here if you see, the value of K is neither 1 and it is neither 0, that is, it is somewhere in between 0 and 1. So this is the case where you get the mutual induction that is between some minimum and some maximum value. So K can be, the formula for K is K equals to M upon under root L1 by L2, where M is the coefficient of mutual inductance of the two coils, and L1 and L2, they are their coefficient of self-inductance of the two coils. Right, children, here we are having one more formula with which we can find out the value of coefficient of coupling. So children, we know that in primary coil we are passing current. So the current is I1. Because of this current, magnetic field is produced, and this magnetic field, because of this magnetic field, magnetic flux will be linked with the secondary, right? So the coefficient of coupling can be related as the flux in the secondary upon flux in the primary. So the ratio of the flux in the primary to secondary can be your coefficient of coupling. So children, with this unit is over. You have completed chapter number 6, that is electromagnetic induction.